Real quick, let's do problem 21 on page 220 in chapter 8. And here is the problem in the book. Let's zoom in. It says, the tires of a car make 65 revolutions as the car reduces its speed uniformly from 95 to 45 kilometers per hour. The tires have a diameter of 0.8 meters. What was the angular acceleration of the tires? And B, if the car continues to decelerate at this rate, how much more time is required for it to stop? That's to go from 45 kilometers per hour to 0. Okay, so I've set the problem up here already and given, find, and solve. Zoom out. Okay. So let's do it. All right. And I want to know what the angular acceleration is. Well, let's see. I know from the initial velocity, I can figure out what the initial angular velocity is. From the final velocity, I can figure out what the final angular velocity is. And I know that, I know the radius. And I know delta theta. Now, I don't know time, and I'm not given time. So I'm going to use the kinematic equation that doesn't have time in it to solve for angular acceleration. And that's how I choose. I look at what do I know, and that sort of thing. So I know that omega squared equals omega naught squared plus 2 times the angular acceleration times delta theta. That's the fourth kinematic equation that you should have on your list. Okay, so now I'm going to solve for this. This is going to be omega squared minus omega naught squared. Just bring that to the other side and then divide by 2 delta theta. Now I want this to be in radians per second squared. So I've got to do some conversions here. First of all, let's figure out what omega final is. Well, that's V final over R. So omega equals the velocity over the radius. Okay, well, the velocity is 45 kilometers per hour divided by a radius. Now, it said a diameter of 0.8 meters. It's really easy to make a mistake and use the diameter. So what I do when I write down what's given, if there's something simple like that, I just convert it right away to the radius. Because that's what I want to use, the radius. So the radius is 0.4. So this is going to be 0.40 meters. Now, here's what I got to do. I got to convert this to meters per second. So I know in 1 hour there's 3,600 seconds. And I know in 1 kilometer, there's 1,000 meters. And now I cancel everything out. Kilometers, I'm left with meters per second. And then I'm going to divide by meters. And that gives me per seconds, which is radians. So now I'm ready to figure out what the final angular velocity is. So that's going to be 45 divided by 3,600 times 1,000. That's 12.5. I'm going to divide that by 0.4. And I get 31.25 radians per second. You all agree with that? Okay. See, I had to go from the linear velocity of the car to the angular velocity of the wheel. Now I've got to do the same thing for the initial velocity. Now this is all the same. So I'm just going to save a little time by just taking 95 divided by 3,600 times 1,000 divided by 0.4, and I get 65.97 or 66.0 radians per second. Does that agree with what you guys did? Okay. Now, what about delta theta? Well, delta theta is, if this is in radians per second, then I got to get this in terms of radians, or things don't work. All right, so I've got, what have I got? 65 revolutions. Well, 1 revolution is 2 pi radians. And I get 408.4 radians. Probably carried too many digits there, but oh well. So now I'm ready to figure out what alpha is. It's omega squared, it's 31.25 radians per second. Square it, minus 66.0 radians per second. Square that and divide it by 2 times 408.4 radians. And let's see, 31.25 squared minus 66 squared. That gives me a negative value, and I'm going to divide that by 2. And then I'm going to divide it by 408.4. And I get negative 4.14 radians per second squared. And that's my answer for part A. Okay, now part B. Well, I want to know the time to stop. And now I can go ahead and use linear, velocities if I want to. Or I can use angular. Actually, I'll just use angular velocity because I know what alpha is. And I know what my, so what I'm going to do is say, well, omega equals omega naught plus alpha t. But now I'm switching this, right? My initial angular velocity is now my final angular velocity. It's the 45, or I'm sorry, it's the 31.25. And then my final angular velocity is actually 0. Right? It says how much more time does it take for it to stop? So I'll solve for time. Time equals omega minus omega naught over alpha. Well, what is omega? It's 0. And the additional time starts after we've reached that 45 kilometers per hour, or after we've reached the 31.25 radians per second. Divide that by negative 4.14 radians per second squared. And so, am I still on screen? Yeah. Okay, so that's going to be and I think the answer should be 7.55. What was the answer in the book? 7 point what? 7.6. Yeah. I'm rounding it to 7.5, 7.6. I think it all depends on how much you rounded this off. So that's rounding difference. I have a rounding difference with the book. But remember, this last digit is always kind of, and these are all 2 significant figures. So I really should have rounded this off to, 4.1. But, oh well. But, and there's our time. What's the big picture idea? If you have a car and you know the linear speed of the car, if you know the radius of the wheel, that wheel is in rolling motion. So you can figure out the angular velocity of the wheel, and all the acceleration of the car, the initial and final velocity of the car, they can all be related to the initial and final angular velocity of the wheel and the angular acceleration of the wheel. They're all related by that, V equals R omega, alpha equals, A equals R times alpha, and so on. Any questions? That's That is all.